Hello everyone, and welcome to the beginning of a condensed series about the fundamentals of physics. Physics, like many other fields, is a broad definition of disciplines and has quite a lot of subfields into which it branches out. In this series, I'll be following the curriculum of introductory physics taught in high school. My goal is to educate, through animation and explanation, how the different aspects of physics interact and mesh together. For the time being, this series will focus strictly on mechanics, which is a study of the relationships between forces, matter, and motion, but I may later include episodes on other subfields. Without further ado, let's begin. The first unit of physics generally focuses on kinematics, or the study of how things move. We begin our journey with some definitions. In physics, every single value you are going to derive or use falls into one of two categories. Vectors are a handy way of describing both a magnitude, or length, as well as a direction in which it is pointing. You can think of vectors in terms of any direction really, from point A to point B, north, east, south, west, or even numerically, such as 43 degrees up from the x-axis. The other type of quantity which you will be dealing with are scalars, which should be much more familiar. A scalar is any number which you can point to on a number line. They can be used to describe quantities which don't really have a direction, such as the statement, there are 3 cars. One of the fundamental relationships between scalars and vectors is that scalars can scale vectors. That is, multiplying a vector by a scalar yields a new vector which is stretched or compressed. Notice how all the scaled vectors still lie on the same line. On their own, these definitions are quite pointless, so it's time to actually get into some physical quantities that you might want to measure. One of the fundamental properties of objects in our universe is their position. Position is a vector quantity, and it can be written as an ordered list of numbers which describes the object's location along the x, y, and sometimes z axes. Take the position of this dot, for instance, at 2, 2. The blue vector is the vector which describes its position. We can move this dot around, and the position vector will always be pointing at where the dot is. As you can see, you can split the position vector into its x and y components separately. The second quantity, displacement, is also a vector quantity, which signifies the change in the position of an object. Displacement is a path-independent quantity. But what does that mean? Suppose a simpler one-dimensional set of 3 movements. If we combine the vectors which signify these movements, we can see that the dot is right back where it started at. This means that adding these 3 vectors yields 0, and thus the displacement is also 0. However, if we lay out these vectors end to end, we can see that the total length of them, and thus the total distance at the point traveled, is equal to 10 meters. Another quantity that comes up often in physics is the velocity vector. The velocity simply signifies the change in position over time. If we have the displacement an object has underwent, as well as the time that it took to undergo that displacement, we can calculate how fast and in what direction the object was moving on average. For instance, let's take this set of 3 other movements over 3 seconds. We can see that the dot is now 4 units to the left of where it started, and because it took 3 seconds to travel, we can calculate with our velocity formula that v is equal to -1 1/3 meter per second. Another quantity, speed, is similar to velocity, but unlike velocity it is a scalar quantity, meaning it only tracks the magnitudes of the movements. We calculate it by taking the total distance moved and dividing it by the time, which yields 3 1/3 meter per second. Finally, our last basic quantity is acceleration, defined as the change in velocity over time. This simply means that if we know the initial and final velocity, as well as the time it took to go from one to the other, we can find out at what rate the velocity changed, or acceleration. In this example, we accelerated from 0 meters per second to 10 meters per second over 2 seconds, which means that the dot was accelerating at 5 meters per second squared, which essentially means that its velocity was changing by 5 meters per second per second. In the last unit, we established that velocity is the change over time of position, and that acceleration is the change over time of velocity. But what does that really look like? Here's a graph of the position of an object over time. As we play the time forward, we can see that the position of the dot on the left changes based on the value on the graph. As such, we can name this graph x of t. But what happens if we want to take the derivative of it? Because the x-axis of our graph is time, we can say that the derivative signifies the change in position over time. As we learned in the last unit, this is the definition of the velocity, so we can call this new graph v of t. Let's add a slider to signify the value of v over time. As we play the simulation, notice how the blue dot on the left essentially drags the white dot along. The connection here is that the sign of the velocity dictates the direction in which the white dot is moving, while the magnitude, or absolute value of v, dictates how fast it's moving in that direction. What if we wanted to differentiate the velocity graph now? Well, remember that because we are working with time as our x-axis, this derivative signifies the change in velocity over time, which we previously defined as acceleration. If we now draw out all three values on a number line, we can see how the relationship between the blue and white dot also holds between the red and blue dot. So we can see how there are inherent links between position, velocity, and acceleration. Namely, we can see how differentiation lets us get from one of the fundamental vector quantities to others, such as position to acceleration. But is there a way to get it back along the chain? Well, if you're a calculus student, you might immediately recognize that, according to the second fundamental theorem of calculus, there is an operation we can perform to essentially reverse differentiation. By taking the integral of acceleration or velocity with respect to time, we can essentially move back up the chain to another quantity. But what if you haven't studied calculus or you don't remember your differentiation and integration rules? We can look at these relationships in a more graphical sense. Here is our position graph once more. If we take a point at, for instance, time is equal to 1, we can see that the position is negative 2 meters. Now, if we draw a line that touches the graph at only this point, otherwise known as the tangent line, we can see that the slope of this line is the same as our velocity at that point. As long as the graph of the position is continuous, this holds for every point along it. What about acceleration? Well, if we take a graph of the velocity, we can perform the same trick to figure out that the acceleration is the slope of the line that is tangent to the velocity graph. But what if we want to go the other way? Analytically, we would use the integration function, but graphically we can think of integration as finding the area that is bound by the function we are integrating and the x, or in this case, t, axis. Let's say you want to find the change in velocity from where the acceleration graph intersects the t-axis to t is equal to 1.5. We could either perform numerical integration or simply find the area of this triangle formed by the graph on the t-axis. Performing either of these methods yields 2.0825. But what does this number mean? Let's quickly show the velocity graph. If we show the graph's value at these two times, what is the change in the value between these two times? Well, we have it right here, the result of the numerical or graphical integration that we just performed. In the last unit, we talked about position, velocity, and acceleration as functions in terms of time, but what applications do these three functions have? In this unit, we will look at the properties of uniform accelerated motion, or motion where the acceleration equals some constant, including 0. We can begin by deriving a general equation. By integrating our constant acceleration value with respect to time, we get a new equation that deals in terms of velocity. This equation simply tells us that the velocity is some constant value plus the acceleration times time. Generally, we think of that constant as being the initial velocity that an object is moving at, so that we can use this function to calculate the changes in velocity over time. Make sure to keep this specific function in mind for later. We can continue the process by integrating our new function, which yields another equation with both velocity, acceleration, and constant terms. Just like before, we are going to treat the constant c as being the initial position. As such, we have just derived a function for the position of an object in terms of its initial position, velocity, and acceleration, provided that the acceleration is constant. This is our first equation of uniform accelerated motion. Remember that equation from step 2? Well, this is actually the second equation that we can use. By combining these two equations in various ways, we can derive 3 more equations to round out our arsenal. We can then use these equations to solve any problem that relates to motion that has a constant acceleration using the 5, 4, 3, 2, 1 rule. These equations share 5 common variables, and each of them only deals with 4. As such, you only need 3 given variables to solve for the other 2. Once you do that, you end up with one solved problem. One final consideration for this unit is when you're dealing with the motion of more than one object. In this case, you can set them to be on the same coordinate plane. Then, to figure out, for instance, when and where they collide, you can simply find when their positions are equal. In the first unit, we briefly touched on the idea of vectors. I mentioned that vectors can be described by some angle from the horizontal and their length. But there are other ways to describe vectors as well. One of the most prominent is to resolve the vectors into their individual components. In 2 dimensions, these are the x and y components, and by using a little bit of trig, or looking at them graphically, we can determine what those 2 components are. But what about 3 dimensions? Here is a representation of 3-dimensional space projected onto your 2-dimensional screen. As you can see, all 3 axes in the 3 dimensions are orthogonal to each other. We can use this fact to define a vector of length 1 in each of the principal axes x, y, and z. By defining these 3 unit vectors, we can use a combination of them to get to any point in space. Take, for instance, the vector a, which has components 4, 2, 1. By taking a combination of 4 I hat vectors, 2 j hat vectors, and 1 k hat vector, we can express the same point at which a is pointing. With that out of the way, let's return to the simpler case of 2 dimensions. Let's draw 2 vectors, a and b. If we want to figure out where a combination of these 2 vectors points, or in other words their sum, we can use our new unit vectors. By resolving these 2 vectors into their components, and adding those respective components, we can get the x and y values of our new vector. If we draw it on the grid, we can see it points in some vague combination of the 2 vectors. Another way we can add vectors together is by doing so graphically. Because vectors represent the same value regardless of where their tail is, we can simply move the tail of vector b to the tip of vector a. Then, our new vector a plus b is going to be at the tip of b now. This method is aptly named tip-to-tail addition. What if we wanted to subtract these vectors? Well, mathematically, subtraction is just addition by a negative number. In this case, we have a negative vector, which simply means we flip the signs of each of its components, which has the effect of making a new vector of the same length, but pointing in the opposite direction. By adding a and negative b, either graphically or analytically, we can get the new vector a minus b. Lastly, we briefly touched on this subject in Unit 1.1, but it's important to reiterate the point of scalar vector multiplication, as it's a central topic in later units. When you have a vector a, multiplying that vector by a scalar is equivalent to multiplying each of the vector's components by that scalar. This essentially has the effect of scaling this vector's magnitude, but keeping the direction the same. If the value you're scaling by is negative, you first flip the vector's direction and then apply the scaling transformation. But, in all cases, the vectors still lie on the same line, and scalar multiplication will never change the line on which the vector lies. Imagine that you are in a 2-dimensional world and you throw a ball. What trajectory does the ball follow? The people who are already familiar with the ideas of projectile motion will likely say that the ball follows a parabolic shape. But how can we describe the motion of the ball through these 2 axes simultaneously over time without introducing a third time axis? The answer is to split the motion of the ball over time into its 2 separate axes and to look at them individually. Let's start with the motion of the ball on the y-axis as a function of time. We can draw the graph of its y position and determine that it too is a parabolic shape. This makes conceptual sense, as the ball will first decelerate until it reaches the peak of its trajectory, and then accelerate until it hits the ground. To figure out what to do with this information, let's insert the first and second derivatives of this graph and see what the velocity and acceleration look like. As you can see, the red line, which shows the acceleration as a function of time, is completely horizontal, meaning that the acceleration must be a constant value. As such, we can use the 5 kinematics equations that we derived in Unit 1.3 to solve for whatever we need to find, such as when the ball is at its peak or how long it will fly. On the other hand, we have a graph of the x position as a function of time. By performing the same derivations that we did for the y position, we can discern that the acceleration is actually 0 for the x-axis of the object. Therefore, we can simply use the average velocity equation, which, by plugging in time, we can figure out how much the object has moved in its x direction. One important thing to note is that for both of these axes, you need to use the same time variable, as these movements are happening over the same time period. There are two important considerations to two-dimensional motion that you must think about when solving these problems. The first is that projectile motion generally deals with some gravitational acceleration. For the most part, it will be equal to the acceleration due to gravity on the surface of the Earth, which is equal to negative 9.81 meters per second squared. Many classes, and specifically the AP test, will generally round this value to negative 10. The other consideration that you must think about is asking what solutions make sense. Because projectile motion often involves solving quadratic equations, more often than not you will get more than one answer. To help not give an answer that doesn't make sense, such as one where time is negative, consider labeling the region of the graph where the motion will take place. In kinematics, we often explore the idea of circular motion, where an object moves along a circular path. We'll begin with uniform circular motion, where an object moves along a perfectly circular path at a constant speed. Notice how I use the term speed instead of velocity here. This is an important distinction to make. As you can see, the velocity vector actually changes direction as we move around the circle, but the point still stays at the same speed. If the velocity is changing, then there must be some source of acceleration. In uniform circular motion, the only source of acceleration points directly in towards the center of the circle, and it is called the centripetal, or center-seeking, acceleration. It always points towards the center and makes a right angle with the tangent velocity vector. One of the main questions we like to ask about circular motion is, how long will it take to perform a single revolution around the center point? This quantity has an official name in mechanics, and it is the period, symbolized t. We find this value by dividing the total distance the object moves by the speed with which it moves. The second question is, what really is the value of the centripetal acceleration? Well, according to the AP Physics C equation sheet, it is equal to the velocity squared over the radius of the path along which the object is traveling. This might seem like a pretty arbitrary equation, so I will link a proof to this fact in the description. I highly recommend going over the proof to understand why an object in circular motion moves in the way it does. These two formulas are the only ones you will need for uniform circular motion, as you can derive the values of other quantities with the information you're given just by rearranging and fiddling around with them. However, not all circular motion involves moving at a constant speed. Take this motion, for instance. The dot speeds up as it approaches the left and right sides of the circle, but slows down at the top and bottom. What equations can we use to determine its motion? Well, something we can do is look at how the acceleration and velocity vectors change as the dot moves along the circle. Let's follow the dot around the circle for one rotation and see how these vectors change. As you can see, the acceleration vector tilts back and forth and changes the length of the velocity vector. Notice, however, how the velocity always stays tangent to the circle along which we are moving. Because of this fact, it is quite helpful for us to change our coordinate system and add two axes. One of them, the perpendicular axis, moves from the center of the circle to the edge, while the tangential axis is defined as the line that's tangent to the circle at where our dot is on the circle. At any point, by splitting the acceleration vector into its two components relative to these two axes, we can get a centripetal acceleration, which, as we discern in uniform circular motion, does not change the speed of the object that's moving, as well as a tangential acceleration. In high school physics, the tangential acceleration will be constant, which means that we can use this tangential acceleration, along with the speed that we derive from AC is equal to v squared over r, to solve for the final tangential velocity. The last important factor to remember is that this splitting of components on our own axes works at any part of the circle, and all that changes is the orientation of our axes. Thus, the formula for solving non-uniform circular motion problems is to consider the centripetal and tangential acceleration as acting on different things. One acts on the change in direction of the velocity, and the other changes its magnitude. Oftentimes in physics, when we are talking about the motion of objects in space, we like to set some sort of arbitrary origin and perform our calculations with the assumption that space is fixed and that the objects are moving within it. However, this is not always the best way to solve a problem. For instance, take these two boxes. What are their positions? If you were to use this arbitrary origin point as your reference, or in other words, set your frame of reference to be stationary between these two boxes, you might say that the box on the left is 2 meters to the left of the origin. However, if we move the frame of reference to be the right box, suddenly, despite the boxes not having moved relative to each other, we could say that the box on the left is 4 meters left of the origin. This is the guiding principle of relative motion, the fact that we can change in terms of what object we see the world. Let's extend this idea to velocity. Assuming we have a ground plane with a conveyor on top of it, and on top of that is a ball which is rolling to the right. We know that the conveyor moves objects along at 2 meters per second, and that the ball is moving at 5 meters per second. The ground, as a consequence of it being our reference frame, remains stationary. Let's see what happens when we play the simulation forward for a second. This makes sense. The ball moves 5 meters in 1 second. What if we switch to the reference frame of the conveyor? Well, then the velocities will be shuffled about in such a way that our conveyor is now at rest. However, if we run the simulation, something weird happens. Because we only care about the top surface of the conveyor, we can see that in the time it took the ball to move 3 meters, the top of the conveyor also moved 2 meters, which makes sense as their combined velocities still equal 5 meters per second. What if we go one step further? In the reference frame of the ball, it is completely stationary, and everything is moving around it. Notice, however, that the end position of the ball is the same relative to everything else in our little world. From these observations, we can derive a general formula for the behavior of relative velocities. Whenever there are 3 objects which move with relative velocities, we can discern the velocity of one of the objects, provided we are given the other 2 using this formula. Let's use it to find the relative velocity between the ball and the conveyor. This idea can also be extended to acceleration. If we have 2 objects accelerating at the same rate as shown, by switching to an accelerated frame of reference centered around one of them, we can see that the other one doesn't move at all in relation, and that they have no relative accelerations, and thus no relative movement. And that's all for Unit 1. If you made it this far, great! This is my first time working with mathematical animation, so please leave any commentary, questions, criticisms, and especially mistakes I made in the comments, and I'll make sure to address them for the next video. If you like the content, make sure to look out for the continuation of this series in the coming weeks. Thank you for watching.